as engineers, we need to be able to perform calculations to work out forces and distances, and also to be able to use those calculations to actually calculate how to balance a beam with different loads on it. So that's what this lesson's all about. Let's get started. So, moments. Most machines use leverage to some extent. And this means we can greatly increase the force that we can apply on an object. And you've got a picture there of a guy tightening up a nut on some sort of vehicle using a great deal of force over a long distance. And the turning effect that you produce is called a moment. And the aim of today's lesson is for you to be able to calculate moments on lever systems and then extend this idea to follow a procedure to use moments to balance loads on a pivot. So first of all, the moment of a force about any point is defined as the force times the perpendicular distance from the line of action of the force to that point. We've got an example of it below. We've got the perpendicular distance, which is the line from the centre of the nut or bolt in this case to the point where the force is actually applied. And the moment is simply the force times the distance. Unfortunately, it's one you're going to have to remember. It's not on the formula sheet. So let's take a simple example. We can calculate the moment on a nut when a force of 250 newtons is applied to a spanner which is 0.18 metres long. So first of all, we write down the moment equation. Moment is force times distance, and then we can simply put the numbers in. In this case, 250 newtons, the spanner is 0.18 metres long, so you multiply the two together and you get 45 newton metres. That's the moment that's actually being applied to that nut. So here's the first practice question. So what I'd like you to do is to have a go at these two questions here using what we've just discussed, and then when you finish them you can restart the video. So have a go at the questions and see what answers you get. Pause the video. Okay, so having had a go at those questions, the answers you should have got are 112.5 newton meters for the first one and 480 newtons for the second one. If you got those answers and you're happy with how you arrived at them, skip on to the next section. If not, let's go through them. So for the first question, what you need to do is to calculate the moment when a force of 250 newtons is applied to a lever 0.45 metres long. So let's draw it out. Got our lever there, 0.45, and then a load of 250 newtons. So the moment is force times distance. Force times distance. So in this case it's going to be 250 times 0.45 gives you an answer of 112.5 Newton meters, because it's force in newtons times distance in meters. The second one, it says a bolt requires a moment of 120 Newton meters to loosen it, and the spanner is 0.25 meters long. How much force is required? So for this one here, we draw a quick simple spanner here like this, and we know the moment there is 120 Newton meters. The distance is 0.25 meters, and we've got to find out the force here. So using the same equation this time, we know the moment is 120. Force we don't know, we'll call that F, times the distance 0.25. So rearranging the equation, force equals 120 over 0.25, which comes to 480 newtons. Okay, so what we need to do now is to move on now and look at balancing forces. First of all, a point to remember: the greater the distance, the greater the moment for a given force. Now then, balancing forces. This is where we're using the same principle of moments to actually work out how we can balance a beam with different loads on it. And the first thing you've got to remember is the principle of moments. And the principle of moments is that the sum of the clockwise moments equals the sum of the anti-clockwise moments. In other words, on a simple beam like the one we've got shown at the top of the slide, the sum of the things trying to turn it one way equals the sum of the things trying to turn it the other way for it to balance. And this is known as the principle of moments. Obviously it works both ways round. You can have anti-clockwise moments equals clockwise moments. I've just put the arrows on there just to try and make it a bit clearer really. So that's the principle of moments. And this is how we can actually use it. We've got a beam here which has got two forces on it which are different distances from the actual pivot point, and for it to balance, force 1 times A must equal force 2 times B. So if I go on to the next slide, we can do a simple calculation. So I've got some real forces in now. I've got 15 newtons on the left hand side. We've got a distance of 1.5 meters from the pivot, and then an unknown force F on the other side, which is 3.5 meters from the pivot. So the first thing to do is just write down your statement of the principle of moments, which is anti-clockwise moments equals clockwise moments. And then you can start putting the numbers in. So all the things that are trying to turn it anti-clockwise, I'll put a little arrow in here just to make it a bit clearer. That's trying to turn it anti-clockwise, the 15 Newton load. So therefore, on the other side where the unknown force is, which is trying to turn it clockwise. So what we can say is that 1.5 times 15, which is, 15 newtons times 1.5 meters, is trying to turn it anti-clockwise. That equals the clockwise moment on the other side, which is F times 3.5. So all you need to do is to multiply 1.5 times 15 to give you 22.5, divide that by 3.5, and you get 6.43 newtons. That's the force on the right hand end, and that should balance the beam. So here we have a practice question for you to have a go at. Similar kind of thing. So calculate the force on the left hand side of the beam this time. And first of all, remember to state the principle of the moments. So have a go at this. Pause the video. Okay, so the answer you should have got for that problem is 6.25 newtons. If you got that, well done. Skip on to the next section. If you want me to go through it, stay online here. Okay, so here we have practice question 2. So let's go through this. So calculate the force on the left hand side to balance the beam. So that's the force up here. First state the principle of the moments. The first thing to say then is clockwise moments equals anti-clockwise moments. In most exams you'll get a mark simply for stating that, even if you do nothing else. So let's go through it. We'll start on the left hand side. The moment here is acting that way, so we're going to try and tilt the beam in a anti-clockwise direction. So on the anti-clockwise side we say F times 14. On this one over here, this is trying to turn the beam in a clockwise direction, so it's trying to do that with the beam. So that goes on this side of the equation, and we've got 2.5 times 35. Therefore, all you need to do is to calculate through. So F equals 2.5 times 35, whatever that comes to, over 14 in this case, and that gives you 6.25 newtons. Okay, so let's move on to the final part. Now, of course, not all systems are as straightforward as having just two loads on it, one either side of the pivot. You can get more complicated systems, and here we're going to look at a more complex system here. So here we have a simple system here to calculate the force on the left-hand side of to balance the beam. So again, we go through the same procedure again. We state the principle of moments. Clockwise moments equals anti-clockwise moments. And I generally find for these types of problems, it's best to work from one side to the other. So from left to right. So look at each load and work out which way it's going to go and then put it into the appropriate side of the equation. So first of all, the first one we come to, the unknown force, that is trying to tilt the beam in an anti-clockwise direction, and that's 0.8 meters out. So therefore we put in F times 0.8 meters on the anti-clockwise side of the equation. The next force as we go along is the 150 Newton force, and that clearly is trying to turn the beam in a clockwise direction. So therefore, on the clockwise side of the equation, we write down 150 times 1.8. The final force on the beam, the 80 Newton force, again is trying to turn in a clockwise direction. So therefore, we can put in 80 times 3.4 onto the clockwise side. All you need to do now is to rearrange the equation to find F. So 80 times 3.4 is 270, 150 times 1.8 is 272, add those together, divide by 0.8, and that gives you 678 newtons. And that, looking at the problem, is what you'd expect. The force F is clearly acting much closer to the pivot, therefore you'd expect it to be larger than the two forces on the other side further out. You'd expect to have more weight there. So 678 newtons sounds okay. If you'd got a much smaller force F than the 150 or the 80, then you probably made a mistake. You need to go back and just double check your answers. If you put one of the clockwise moments on the wrong side of the equation or something like that, that could easily happen. So that's the way to do that. And here we have another practice question. Same kind of thing. Another beam, and this time find the unknown force F. So as usual, have a go at it. I'll pause the video, and then I'll tell you the answer, and then we can go through it, or we can go straight on. So pause the video now. Okay, so the answer you should have got is 42.7 newtons. If that's what you got and you're comfortable how you got there, well done, go on to the end of the lesson. If you want me to go through it, stay online. Okay, so here we have practice question 3, and we need to calculate the force required to balance the beam. That's this force here. So we start off, as we do with all of these things, by writing down the statement of moments. So we say clockwise moments equals anti-clockwise moments. This means it's easier to set the whole problem up and work it through. So best if you go from left to right. So this is the first force here, and that's obviously going to push down, which means the beam will tend to rotate anti-clockwise. So put a little anti-clockwise arrow there to remind me that this part of the calculation goes on this side. So the moment there is 25 newtons times 4 meters. So put 25 times 4 there. I come to the next one along here, which is the unknown force. That's going to push down, which will tend to rotate the beam in a clockwise direction. And that's 1.5 meters from the pivot, so it's F times 1.5 here. So I'll put a arrow there. And this one as well will tend to rotate it in a clockwise direction. So I put a clockwise arrow here. And this is 3 plus 1.5 is 4.5 metres from there. So we go 8 times 4.5, and that will be added to the other clockwise moment you've got here. Then all you need to do is simply multiply that through and rearrange it. So F equals 100 minus 8 times 4.5, which is 36, divided by 1.5, and that should give me 42.7 newtons, and that's the correct answer. So the main thing is to just follow the procedure and you should be okay.
Okay, so that's the end of the lesson on moments, and hopefully you can see a moment's a very straightforward concept, force times distance. And to get the higher marks, what you need to do is to apply them in more complex situations. And the best way to do that, as I showed you, is to take it step by step. Sketch it out if you need to. Use your pen or to actually work out which is a clockwise and which is an anti-clockwise moment. Take your time, step through the calculation, and you will get good marks. Even if you get the wrong answer, if you've shown you understand the concept, you're clear what you're doing, you will get most of the marks of the question. So that comes to the end of this topic. The next one that follows on from this is simply supported beams. As always, there are some exercise sheets which you should have as a hard copy to go through them. The questions vary from fairly straightforward to much more complex questions, more distinction standard at the end. So if you can't do all of them, it doesn't matter. As long as you've got the basics on there, that's great. So I'll see you on the next video.